Last time we talked about some more calculus of variation stuff, sort of part 2. And I kind of tried to show you guys that stuff from like 2 different perspectives. There was like the classical sort of variational derivative thing, and then we kind of did this dynamic programming sort of derivation of it. So hopefully some combination of that made some sense and stuck. Then we talked about dynamics and energy and how, it kind of makes sense that for a conservative system, you can sort of write down the, kinetic and potential energy and differentiate that and set that to 0 because it's conserved. And then like you can kind of massage that and get your dynamics out. We talked about how like the naive version of that is not coordinate invariant, and so it kind of doesn't work all the time. And so we did this Euler-Lagrange thing instead, and we showed that is coordinate invariant, and then we showed that that can be derived from a least action principle and sort of the calculus of variations machinery. And we talked about Lagrangian mechanics. That kind of falls out of that. And then we talked about, the least action principle. So today, couple things. So first thing is, I got like a bunch of questions about, interpreting the least action principle. And last time I kind of basically argued that it really is just that it sort of is equivalent to F equals ma at the end of the day. And like it's coordinate invariant, has all these nice things, but at the end of the day, there's not a whole lot there. I'm going to try to dig into that a little bit more today and offer at least some sketchy, high-level interpretive stuff on that, and sort of maybe give you a little bit more intuition for what's going on there. So sort of interpretation of the least action thing. Try to make some more sense of that other than the super unsatisfying because the math says it's F equals ma. And then we're going to look at, dig into more of the Lagrange mechanics story. So today we're going to look at the Manipulator Equation, which is the form of this stuff that you most often encounter in robotics. But it really is just the Euler-Lagrange equation kind of reworked and relabeled. So we're going to derive that, talk a little bit about that. Then we're going to talk about how you deal with non-conservative forces in this whole setup. So far we've talked about potentials, right? Potential energy, and then how like minus the gradient of a potential gives you a force. And that's a conservative force, so things that conserve energy. So far we talked about springs and gravity basically. But there's a lot more interesting stuff in the world to deal with. So namely like control torques, right? From motors or thrusters. And things like friction, right? There's all kinds of things that don't conserve energy and can't be derived from a potential function. So we're going to talk about how to like shoehorn that into this whole machinery that we've set up. And then depending on how far we get, we're going to talk a little bit about constraints and coordinates. We'll see how far into that we can get. So first, any questions about anything we talked about last time? Anything in general, homework, whatever? No? Okay. Yeah, all right, so we'll get into it. So first, this kind of trying to give some like interpretive, fuzzy hand wavy arguments for why the principle of least action makes some sense. I like thought about this a bunch and tried to like put a little bit of my own spin on it to try to explain why this might maybe make sense. So last time we did the Euler-Lagrange thing. So I'm going to abbreviate now EL equation. So this guy, right? It's d dt partial L partial Q dot minus partial L partial Q equals 0. And we kind of talked about how, this first term is basically MA. And the second term is basically like minus the grad of a potential. So it gives you kind of your force. So this is really kind of a restatement of F equals ma that, unlike F equals ma, is coordinate invariant. So we can pick whatever generalized coordinates, Q's we want, and it always works, which is cool. So then we kind of talked about how that equation is the first order necessary condition for this least action thing, right? And historically, that's how it went, actually. So historically, it was F equals ma, then this thing actually was come up with as some massaging of F equals ma to make it coordinate invariant. And then later on, Hamilton realized that this was actually sort of KKT conditions for the least action principle. So that's actually historically how it went. So this is first order necessary condition of this optimization problem, sort of min over the trajectory Q of t, this action thing that looks like integral of this Lagrangian thing we talked about before. So we all know, right, this thing is the action, this whole integral, and then this guy's Lagrangian. And then we did the whole thing last time where we took this thing's derivative and set it equal to 0. So let's look at, we're going to sort of split this apart a little bit. So if we define L to be kinetic minus potential energy, this gives us the dynamics of a conservative system, like we said, which ends up being, we're just going to plug this in. So we can kind of break this up into two pieces. So we've got T of Q, Q dot, the kinetic energy term, minus, we can actually break the integral into two pieces, right? So we've got T naught, T final, now U of Q, dt. So if I kind of look at these two pieces separately now, sort of, could we interpret each of these separately? Like what would you say like this first thing is? So the first one's kinetic energy, right? And this is integrating the kinetic energy along the trajectory of the system. So like the way I think we're going to interpret this is it's essentially the average kinetic energy. If I stuck a 1 over T out front, like 1 over big T, right, it would be the average, right? So this is like, essentially, we'll call it the average modulo a constant. Does that sound good to everybody? And so similarly, this guy is the average potential energy of the system over a whole trajectory, right? Okay, so roughly speaking, right, up to a constant factor, this is sort of average kinetic energy, and this guy sort of average potential. Is that cool with everybody? Does everyone kind of get that? Okay, so now like what's happening here, right? Remember, this is a conservative system, so the whole thing has to conserve energy. So the total energy is the same over the trajectory. So the only thing that can happen here is you can trade kinetic for potential energy, right? And so if we think, so let's write that down. So if we think about like, and kind of think about that, sort of intuitively, what will happen, let's think about like a ball rolling down a hill kind of vibe. So we started with a lot of potential energy and a little kinetic energy, say, right? And what's going to happen is, as I roll downhill, I'm going to lose potential energy and gain kinetic energy, right? If I think about the averages over the whole trajectory, what's going to happen is I trade one for the other, and the dynamics are basically, if I think about the average over the whole trajectory, it's going to bring those two values closer together, the dynamics, right? It's going to say, if I roll down a hill, I'm going to lose U, it's going to bring U down, and it's going to bring T up. And they're going to sort of like approach each other in some sense, right? If I trade one for the other. So if I think about it that way, and I think about conservation of energy and blah, 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 the natural dynamics of the system essentially want to bring these two quantities close together. Does that make sense? So what this least action principle is really doing is minimizing the difference between these guys, right? And so remember, these are energies, so they have to be positive also, right? So this, these guys are, I mean, potential could be negative, but that's sort of an arbitrary thing. Kinetic energy is always positive. It's a quadratic form, right? But yeah, I think like interpretation-wise, think about these as two positive quantities, and like the dynamics are basically going to trade one for the other and try to bring them close to each other and make them match essentially, right? As I integrate the system forward. So that's what this equation says, right? It says I want to make these things, minimize the difference between them, AKA make them as close to each other as possible. And if I think about what's going on, that sort of jives with what we expect to happen with like ball rolling downhill. So let's write that down. So this has like u greater than t. This has sort of t greater than u. And they okay, does that make sense? So is that idea, like any questions about that kind of interpretation of this? Sort of average kinetic average potential, and like if I trade one for the other, I'm bringing them closer together, and that's essentially what conservative dynamics do. I'll give it that idea. So one more twist on that idea. So at a minimum of this action thing, we have that sort of gradient equals 0 thing. So let's write that down again and rearrange a little bit. So we can write that as basically d dq of average kinetic energy, say, equals d dq of this guy. So what does that say now? So this is, I just took the first derivatives, right? And like moved one to the other side of the equal sign. So this is the same like first order necessary kind of condition. So what this is saying is that at a minimum, any change that I see in the kinetic energy has to be directly equal by any change in the potential energy. So this is literally just a restatement of conservation of energy now, right? So what this is basically saying is the true trajectory has to conserve energy. So the least action principle, if I'm not at a minimum, I'm not conserving energy, right? Literally the minimization conditions here, the first order necessary condition that where you set the gradient equal to 0 says it has to conserve energy. Does that make sense? So the trajectories that minimize the action are the ones that conserve energy and therefore like obey physics. Okay, that was sort of two interpretations of this stuff. So let's write that down. Change in kinetic energy. So basically a restatement of conservation of energy. And this is only true at a local min of the action. So kind of saying true sort of physically realizable trajectories must minimize the action. To conserve energy. Okay. Any questions about that? Yeah.
All rolling down the hill situation, T and U only became closer together in the middle of rolling down to the bottom. Now they've switched.
Yeah. So what this is, though, remember, it's the average T and U integrated over the whole trajectory, right? So if I'm trying to push them closer together on average, that's the thing to do, right?
But,
like you said, they're closest together in the middle, right? Which is basically the average value of both.
oh,
Does that make sense?
Yeah.
Yeah. Yeah.
This interpretation is not exactly conservation of energy, right? Because the signs should be different by the idea of conservation of energy. Like increment in one should be equal to decrement in other.
Yeah, that's true. So this thing, like technically, right, this gets a minus sign in front of it when you define the forces. So I think it's sort of buried in that. It's a little fuzzy and not like, I'm not being super precise about this. So let's see. This says, yeah.
But that minus is true. Like that is in the definition of your potential energy, right? It's not.
It's in the definition of the, yeah, it is. So what is this saying? This is saying like if I change trajectories a little bit, these guys both have to change sort of together.
Yeah.
So like small changes in you have to think about this some more. So any increase, what this is really saying though is it's saying this is true for like, if I move away from this, if I move away from the optimum, it's saying like these are both gonna sort of get bigger basically by the same amount.
Yeah.
So it's saying like locally at a minimum, they're sort of trading off at the same rate. Make sense? So like small changes in them have to be equal to each other. Like, yeah, this is a little fuzzy. This is not my best explanation. This is sort of me trying to come up with explanations on the fly. So I'm gonna have to dig in on this one a little bit more. But yeah, that's sort of the first thing is definitely right in terms of like this interpretation of the average is coming closer together. That's sort of, and this is sort of like the differential version of that that's saying like, if I took the sort of total kinetic and total potential energy, if I changed the trajectory a little bit, they would basically both have to.
I mean, like the condition is definitely.
Yeah.
There's nothing wrong with the condition.
Yeah. I'll have to think about this some more. Anyway, this is all sort of like hand wavy stuff. That's not, this is intended to get you some like intuition rather than like, you know. Okay, any questions about any of this stuff? All right. At the end of the day, it really is just that the math works out though. That's kind of it. All right, so let's see. Next, I'm going to talk about manipulator equation. Who's seen this before? Just about everybody. Yeah, okay, everyone's seen this before. Who's seen this sort of as a derived from like the Euler-Lagrange equation before? Okay, half or so. Where did you guys do that? Okay, cool. So the story here is all mechanical systems have a Lagrangian of the following form. We have basically a 1/2 mv squared kind of thing. And then this potential energy thing. So it's really just saying that for any mechanical system, the kinetic energy is this quadratic form thing. And the matrix in the middle is called the mass matrix. Or if you're fancy, the generalized inertia tensor. But colloquially, mass matrix. Okay, so let's do a quick example of this to like get a mass matrix and kind of show what we mean by this. So we're going to do the classic cart pull real quick. So who's seen cart pull before? Almost everybody. Cool. So we're talking about a cart with wheels, say, and a pendulum up here. And we're going to have an x coordinate for driving back and forth, and then a theta coordinate for the pendulum. We're going to call this guy mass P up here, and this guy mass C down here, and say the pendulum length L. So the first thing to write down here is sort of the kinematics of the pole position, the pole mass. So we can write down the pole mass position in sort of XY coordinates in terms of these generalized coordinates is, so the X coordinate, right, is going to set the X coordinate of this guy plus a sine theta term. So X plus L sine theta, and then the sort of height of this guy is L cos theta. So now I can write the potential energy down as just U equals mg times the height. So it's m p times g times L cos theta. That's pretty easy. Now let's write down the kinetic energy. So this will look like, so we have the kinetic energy of the cart, which is just 1/2 mass of the cart x dot squared. Then we've got sort of a 1/2 mv squared thing for the pole, and that's going to look like, I'm going to take the time derivative of this guy and then square it. So that's going to be x dot plus L cos theta theta dot, and then minus L sine theta theta dot, and then I'm going to square this guy. So same stuff. We'll just do the. Cool. So if I expand that out, I'm going to get 1/2 mass of the cart plus mass of the pendulum times x dot squared plus 1/2 mass of the pendulum L squared theta dot squared plus mass of the pendulum x dot L cos theta theta dot. So the idea with this sort of quadratic form kinetic energy thing is I'm going to take this expression here and I'm going to just kind of massage it into a form that looks like that. So I've got 1/2, I've got the velocities. So x dot theta dot transpose times some matrix times x dot theta dot. And if I kind of look at this guy, I can just take all the coefficients off these terms. You'll notice that the velocities always show up squared in some way, right? So I just take the coefficients off all those. So the x dot squared term is up here. Then we've got the theta dot squared term in the bottom right. So that's MPL squared. And then this is the cross term. So that's got an x dot theta dot in it. So that's MPL cos theta up here. All right, so basically that's the mass matrix now. Cool. And this kind of works out for every mechanical system you want to write down. Has anyone ever seen a Lagrangian that didn't look like that? Kinetic minus potential energy? No? Okay, it happens, but we won't talk about it here. But not for mechanical systems like we're talking about. All right, so that's all good. Yeah.
Does it depend on the joint in the manipulator or something else? Like you said, it's possible it is like a Lagrange.
So it's possible to have Lagrangians that don't look like kinetic minus potential energy, but not in sort of classical mechanics.
And is it because of something related to joints? Like we have regular joint versus spherical or something else?
No, that always looks like this.
Okay.
Yeah, basically, what we're really just saying is that kinetic energy here is always a quadratic form. It always looks like 1/2 mv squared, basically, right? That's what this says. Cool.
The definition of Lagrangian is not kinetic minus potential, or is just the form of the kinetic or the potential can be different than a quadratic?
So the Lagrangian in classical mechanics always has that form. In like the kind of mechanics we'll deal with, basically always, it always looks like that. In optimization, Lagrangian means something more general, and it turns out in other branches of physics it means something more general and can look different. So basically, in other sort of less classical flavors of physics, kinetic energy looks different. Yep, sometimes there. And also, so yeah, you can have vector potentials in electricity and magnetism. Also in special relativity, kinetic energy doesn't look like that anymore when you get close to speed of light, stuff like that, right? So you can get other kinds of weirder flavors of kinetic energy that don't have that quadratic form flavor, but they're still Lagrangians, and you can still get the dynamics from Euler-Lagrange. In fact, you can do all of physics this way, like quantum mechanics, et cetera. It just gets weirder. Okay, cool. So what are we doing now? So that's just to show kind of this, the carpal thing, how the mass matrix kind of works out. Now we're going to plug this in. And we're going to get this guy. So we're going to get ddt partial L partial Q dot. So I'm going to do this one first. So first off, partial L partial Q dot is just mq dot, right? And then if I take the time derivative of that, I'm going to get something that looks like m of q double dot, so ma, plus this other term, weirdo term, m dot times q dot. And something to mention, right, is that if I have m equal a constant, I only get this term. If m of q if m is a function of q, not constant, then this extra term pops up, right? Okay, so that's cool. Now let's do the other piece. So partial L partial Q, this is going to look like minus partial U partial Q plus, we're going to sort of cheat a little bit here. So this again, this second term, so this first term is the one we know, this is the force coming from the potential. The second term has to do, once again, with derivatives of the mass matrix, right? And in a sec, we're going to kind of smush these two terms together. So basically, what's going to happen if I put these together, so those are the two pieces, I get m of q, q double dot, and then I'm going to group all those derivatives of m things together. So I get this like m dot times q dot. And then I get this partial respect to q, 1/2 q dot transpose m of q, q dot. And then I get the partial u partial q term, and this all has to equal 0. So this is just me massaging around the Euler-Lagrange equation and basically plugging in that quadratic form. The stuff in the middle all has to do with derivatives of m, right? And it turns out these two terms look pretty similar. If I chain rule this guy, I'm going to get like dm dq in here, and this guy's got some dm dq. This is basically dm dq times q dot, right? So both of them involve like a dm dq times a q dot squared-ish thing. Both of them, the reason I didn't write these out in more detail is because they both end up being like third-rank tensor terms, and I take dm dq, so it just gets messy. But what we're going to end up doing is grouping this whole mess together and calling this C of q dot. And this is called the Coriolis term. And it comes from the q dependence of m. So if m doesn't depend on q, this goes away, right? And then this guy over here is typically called g of q, and this is kind of the potential term. And then we know what the other stuff is. So if I write this all together now, my Euler-Lagrange equation is equivalent to this guy. And we call this guy the manipulator equation. And again, it's just a restatement of the Euler-Lagrange equation. This is super common in robotics, and it's the standard thing in most multi-body dynamics software toolboxes that you'll use. So like Bullet, Rojoko, all those guys kind of deal with the dynamics in that form. So you'll definitely see this out there. So let's see. What else is there to say about this? It's just a restatement of the Euler-Lagrange equation. And let's see. So also a lot of the software packages that you'll encounter basically, just as a note, they basically wrap these two terms together. Often is very common, and they call it the dynamic. Yeah.
In the past, when I've seen it, the Coriolis term keeps the q dot on the outside. You just have it nested inside.
Yeah, so there's a few variations that you'll see of this. One is what you just said, where you factor out a q dot. So there's sort of some quirks to that. Basically, if you do that, it's totally fine to do that. It actually, the definition of the C matrix becomes ambiguous. It's actually not clear. So there's sort of multiple q dots floating around in there, right? And it turns out I can basically refactor that expression a whole bunch of ways because it's actually nonlinear in q dot. So I can pull q dot out in various ways. There is sort of a standard way, but there's no consistent definition of that matrix C from software package to software package and textbook to textbook. So the reason I'm just not doing that is because it's non-unique and there's some like iffiness in the exact definition for that C matrix. So yeah, you'll see that sometimes. So let's say that. Sometimes you will see C of q dot times q dot, where this is a matrix. But this is not unique. And then the other thing you will see basically wrapping both the Coriolis term and the potential term into a single C term. And then when they do that, they call this the dynamic bias term. And that's kind of the standard thing in a lot of packages that implement Featherstone's algorithm, like recursive Newton-Euler, things like that. We'll do it that way and call it that. So yeah, there's some fuzziness in exactly how you define this thing. You'll see subtle variations, and especially in the Coriolis term, being written a few different ways. Let's see. Any questions about that? Okay, everyone's pretty much seen that before. So here's one thing that's kind of fun from this is it very nicely shows you the worst case computational complexity of computing dynamics. Has anyone seen this before? Okay, so check this out. So if I want to compute the dynamics, so when I want to compute the dynamics, when I want to simulate the system, I need to solve for Q double dot, right? Like that's the thing I need to compute to get X dot in my integrator, say, right? To simulate stuff. So if I solve this thing for Q double dot, I get, basically I have to move this thing over and solve a linear system, right? Potentially with other stuff. So when I'm doing this, I'm solving a n by n linear system, right? What's the complexity of solving a linear system, an n by n linear system? Cubic, right? It goes like n cubed to solve a linear system. So therefore, the complexity of solving for Q double dot here and ultimately the complexity of doing dynamics is cubic in the state dimension. That makes sense to everybody? Okay, so there's a lot more to say about that. So that's like if I naively treat M as just a dense matrix, but it turns out there's a lot more structure going on. And for a lot of problems, you can actually get this down to O of n linear time, which is, maybe you've heard of Featherstone's algorithm, recursive Newton-Euler, these things. That's what that's all about. Basically takes us from cubic to linear complexity, which is a huge win if you're simulating a complex robot. And that wasn't like definitively proven and like discovered, if you like, whatever you want to call it, until the 80s was when that was like finally kind of legit proven that you could do that in general. Okay, so more to say about that later. So yeah, worst case it's cubic, best case you can get it to be linear sometimes if you're lucky. Okay, so let's do another, we'll sort of like keep carrying through the carpool thing. Oops. Again. And kind of do the whole thing. So we've got the Lagrangian from before, which was, I wrote out the mass matrix and all that stuff. I'm gonna just write it down again real quick. So we've got it handy. That's the kinetic stuff and then the potential stuff here. So if I kind of chug through the Euler-Lagrange stuff, I'm going to get the mass matrix I had before. And let's see, MPL squared. So we get this mass matrix times Q double dot. So that's X double dot, theta double dot, plus a Coriolis term that looks like this. I kind of follow through with all the derivatives, plus a gravity term, aka potential term that looks like this. Equals 0. So I've got M of Q, C of Q, Q dot, and G of Q. And if you kind of look here, right, like this depends on both theta, theta dot. This only depends on theta. This only depends on theta. Right? So that kind of checks out. So the point here is like different pieces of this thing. The reason for like kind of looking at the manipulator stuff in more detail, it's basically sort of like showing you which pieces depend on which sort of elements of the state vector, right? Which is sometimes useful, especially in control applications. Okay, questions about any of this stuff? Cool. All right. So now we're going to talk about, so far we now know how to basically get dynamics for any conservative system. You can like pick some coordinates, write down the kinetic potential energy, Lagrangian, or the Lagrange equation, done, right? So the next thing to talk about is like, what if I have control inputs? What if I have friction? What if I have things that I can't get the force from a potential? So let's do that real quick. And I think like, I would argue this is kind of a hack. Like the sort of standard theory that we've done so far is really pretty and like looks really nice for conservative systems. And what we're basically going to do is sort of like hack it and bolt on something that's kind of made up in order to sort of shoehorn additional kind of non-conservative forces in there. So here's how that works. So conservative forces coming from, say, we'll call this F conservative minus grad U are already included. What we need to do now is, so we have, say, so what we're going to kind of think about here is we already kind of know what the answer should look like here from F equals MA. And so we're going to kind of write that down and then kind of show that it's right. So we can kind of guess what should happen. Other forces. So you've got basically like your Euler-Lagrange thing. So remember, this is basically MA, and then this guy is basically the conservative force term. And if I move it to the other side, it would literally, of the equal sign, it would literally be like minus grad U on the other side. So that's telling you I can just stick whatever forces I want on the other side, basically, as long as the units work out and they're units of force. So I can stick my non-conservative forces over here. Stated like in manipulator equation terms, that looks like this. So equivalent stuff, basically like you can just stick generalized forces on the other side of this. And what we mean by generalized is that they have to be defined in the Q coordinates, right? Okay, so you guys probably seen this before. What we're gonna do next, though, maybe haven't seen before. So this is kind of standard stuff. Now the question is, can I kind of get this into the least action principle? Has anyone seen that before? Okay, so that's a little weirder. Basically, what we're gonna do, and this is kind of the part that's a little bit of a hack, is so basically from like, this conservative force equaling minus grad u, we basically know we need a term to go inside the action integral whose derivative is f, right? So what kind of term should I put in there such that its derivative with respect to q is going to give me f? Sorry? So it's going to be not quite that. Remember, it's this variational derivative thing inside the integral. So I want it's like when I go take that variational derivative inside the integral with respect to q of t, that thing needs to be f, right? So you're almost there. It's basically going to be f times q of t under the integral, right? Does that make sense? Okay, so that's kind of the idea. So we want something that sort of integrates f, whose variational derivative with respect to q of t is f. So what we're going to do then is, so remember our Euler-Lagrange thing is basically this. We've got our Lagrangian. And then we're going to add this term now that's just the external force times q of t. And this thing now has to equal 0. So sort of when I go and do this, remember I got like dl dq times a delta q, dl dq dot times a delta q dot, blah, blah, blah. And I did that trick. Here I'm going to get f times delta q, right? And so when I'm all done, I'm going to factor out all the delta q's, and what's left is going to be Euler-Lagrange stuff plus the force term, right, equals 0. So that all kind of works out, right? That's the idea. So there's one weird quirk to this. Note here, right, I wrote L as a function of q and q dot, like we did before. And when I go dip this, I'm dipping through here with the chain rule. However, this F, we're going to treat this as like an exogenous force, say, i.e. it's some external force that's, we're treating it as only a function of time, i.e. not a function of the state, for the purposes of taking this variational derivative, which is a little weird. But later, if I have like a feedback controller that is a function of the state or whatever, and I kind of plug that in, we can do that. It just so happens for the purposes of like this derivation, you have to treat this thing as like an exogenous force that's not a function of the state for this to work. So that's a quirk. Okay, so if I do this, I get the usual kind of thing that we did before, and I just pick up a force term. So I can kind of write out the first order necessary conditions for this. Will look like, say, d1L times a delta Q plus d2L times a delta Q dot plus this guy now. And then if I do the integration by parts trick, that second term turns into minus, pick up a minus sign, flip the dot. So this guy, and then I get delta Q, and then this guy's all So now I can pull the delta q's off. Oh, I missed a delta q on that first term. So now this basically says Euler-Lagrange stuff, ddt partial L partial q dot minus partial L partial q equals F. If I transpose everything. So anyone seen this before? Nope. Okay, so this thing is called the Lagrange-D'Alembert principle. Has anyone heard of D'Alembert's principle before? Show of hands. Anyone heard of that before? Sorry?
Used to call it D-Lambert principle.
Oh, it's D'Alembert, yeah. If you speak French, which I don't, but that's how you pronounce it, ish. But you've heard of this before, at least. So there's another name for this too. That's the principle of virtual work. Has anyone heard of that before? Okay, so so I'm going to write this in a slightly different form and show you where that comes from. Okay, so the non-conservative term that we added in there has units of work, aka force times distance. So this, we're gonna write this guy down as its work. So this is really the work done by this non-conservative force, right? It's the dot product of the force with like the displacement, right? And we integrate it up along the trajectory. And when I take the variational derivative of just this term, I get, if I do the like standard variational derivative kind of thing notation, I get sort of variation of the work equals F dot delta Q dt. And, you know, the way we've been doing it, we've been basically writing it as like d work dq, where I kind of divide through here more or less. The thing in the middle is what's left over. The classical sort of lingo of calculus of variations and classical mechanics, you call this sort of delta Q thing, this like infinitesimal perturbation of the trajectory, a virtual displacement sometimes. And so therefore you call this work thing a virtual work. It's just like weird names for these things. So let's see. So that's just where the name comes from if you were a QA this. This is like a very old school kind of classical, yeah.
Delta Q disappear in the second term, where you have delta Q dot.
Where?
If we're taking partial derivative, derivative with respect to dq, second term that we have on the first line, very first line, above.
So,
Yeah. That in which you have d1 and
sorry, here.
yes,
Okay, so
the second term there.
this term?
No, yeah, this line, the second term. So yes.
Okay.
The
Did I-
second term, where is the dq term? I thought-
DQ dot?
Yeah, how did the dq dot of
So I did partial L, partial, I just chain ruled it. So I do partial L, partial Q times delta Q.
I thought we were taking partial with respect to d by dq.
I'm taking partial derivatives of the stuff inside here with respect to Q of T. Right, so this guy's a function of Q and Q dot. So I get partial respect to Q times delta Q, partial respect to Q dot times a delta Q dot. And then the next line, this is kind of the derivation we did of the Euler-Lagrange equation before, which is why I went kind of fast and skipped stuff. But basically, so this is what we get by just kind of doing the chain rule. And I want to get rid of this delta Q dot term and turn it into a delta Q term so that I can actually sort of factor it out and compute the derivative, right? So what I do then is I do this integration by parts trick. And this should be a minus sign. So I did this in class a while back. Basically, the trick is, were you here for that discussion? The calculus of variations discussion with like, okay, so go check those notes. Basically, there's a trick between this line and this line where I use integration by parts, which I did at length. So just go check those notes. If you get stuck on that, let me know. Basically, there's a trick here where you can flip the derivative on a product like this. It's backwards product rule. So if I like take an expression where I have like u times v, and I differentiate it, I get u dot v times uv dot. If I integrate both sides of that, I can like get a trick for flipping the dot. So that's what this is. I'm moving the dot from here to here. That's what this is, right? I remove the q dot, I move the dot to this term, and then I pick up a minus sign and a boundary term that ends up being 0 for reasons that we discussed before. So that's what that is. And that's how you get the classic Euler-Lagrange equation, this guy. And now we got this extra forcing term. This whole mess is this Lagrange-D'Alembert principle. And you'll also hear this called principle of virtual work. And you'll also see this written sort of a bunch of different ways. Okay, any questions about this? It's how you get forces that aren't conservative into the whole variational mechanics setup. So the reason we're doing this is less because of this and for reasons of like, it turns out you can use this stuff to make really good integrators. That's where we're going with this, but we're not quite there yet. Well, you might not have seen this before. Okay, so let's go back to the carpool one more time and plug this stuff in. So let's assume we have a motor on the cart. That's bad notation overloading. So let's put that with a lowercase then. So we've got this guy, we've got our cart. Cart has wheels, pendulum, coordinates. And now we have this force on the cart in addition to what we had before. So what's going to happen now, you can kind of derive it the way we did, but maybe I'll kind of skip through some of this and do it fast. You'll get the mass matrix we had before, which now is m of x theta times x double dot theta double dot. You'll get c of q, q dot, g of q, just like we had before. And then this, we're going to now have this new forcing term on the right-hand side that's going to have this cart force acting in the x coordinate, right? So that's what that looks like. Cool. Any questions about that? Straightforward, you guys have seen this before. Cool. So yeah, you can, I'll leave it as an exercise for the adventurous among you to kind of chug through this Euler-Lagrange stuff, virtual work stuff to try to get that last term to pop out. But we'll do a little bit more with this later. Okay, so the last topic of the day is constraints and coordinates. So So far, we've been dealing pretty much exclusively with minimal coordinates. What does that mean? Anybody?
Joint space.
Yeah, it usually means joint space in robotics applications, but there's a specific technical meaning for minimal coordinates. Yeah, that's right. Yeah. So it's the least number of coordinates you can possibly have to describe the system. So it's exactly the same number of coordinates as degrees of freedom. So that often makes sense. In particular, it's usually the right move for sort of fixed base classical robot manipulators where you're stuck to the world frame and you have a bunch of links and you have joint angles and everything's kind of nicely described in terms of joint angles. That makes tons of sense in that kind of setting. And that's the standard thing. But it can make less sense in a lot of more complex robotic systems that have floating bases. So like mobile robots, and that have, in particular, closed loops can be very messy to deal with in this way, and it becomes ambiguous how to define your coordinates, and there's all kinds of weird stuff that can happen. So think like a 4-bar mechanism like this, those cause problems. So it turns out that often the dynamics can be simpler with more coordinates. And sort of better behaved also, numerically. What's a good example of that we've already seen? I think SE3. Yeah, so Euler angles are a minimal representation of rotations, right? Because there's 3 Euler angles, 3 degrees of freedom, but they have singularities and they're super nonlinear and gross. And pretty much anytime you deal with a real floating base system that has large rotations, you don't want to use Euler angles because they're terrible. And instead we want to use something like quaternions, where you've got an extra coordinate, but now things are like kind of quasi-linear and well-behaved and they're not singular and all that kind of stuff. But now we remember when we did the quaternion stuff, you pick up a new constraint, right? So now that's 4-dimensional, better behaved, but you also have this unit norm constraint on the quaternion, right? So that's an example of this we've already seen. Turns out there's tons more situations where that comes up. So we need to have like a constraint for each additional coordinate, basically, to sort of remove the fake degrees of freedom. Okay, so we've kind of already seen how to handle constraints in the Euler-Lagrange setup, in the variational kind of derivative setup. When we did the hanging chain, remember we had endpoint conditions that had to be satisfied, and we kind of threw a Lagrange multiplier term in there, right? So that looked sort of like this. So we had, say, min with respect to q of the standard thing, say subject to some constraint c of q equals 0. And then what I did was write down sort of same kind of first order necessary kind of thing with the Lagrangian guy plus a Lagrange multiplier term. And this whole thing has to equal 0, right? And so now if I kind of chug through the Euler-Lagrange stuff like before, I get the same kind of stuff, but I pick up a new extra term. And remember, I also still have the original constraint. Remember when we did like kind of the optimization stuff, this is the partial respect to Q. I also have to take the partial respect to lambda and set that equal to 0, and that gives me back the original constraint, right? So I got both of these things to deal with. Okay, so looking at that real quick, remember this is a force, right? So this term also has units of force. In particular, this constraint thing here ends up being unitless. And the Lagrange multiplier ends up being units of force. So usually what we say here is this thing is our constraint force. And then this guy is our constraint Jacobian. Usually write this J of Q in roboticsy settings. And so putting this all together in the manipulator equation, you get stuff that looks like this. So you'll get, I mean, you can have your forcing term like we had before, and then you'll get a new term that looks like J transpose times lambda when I kind of set everything up as column vectors. Cool. Has anyone seen this before with this new kind of constraint term over here? Yes? Cool. Who hasn't seen this before? Okay, few people. Okay, so if I want to now simulate the dynamics of this guy, I need to solve this guy for Q double dot just like before, but I also need lambda, right? I need to actually solve for lambda and plug it in to this equation to get Q double dot. So how do I find lambda? Anyone have any ideas? How do we do it when we did sort of standard optimization? Yeah. So that's what this is, right? That's what this line is just that, right? Set the derivative equal to 0. And then if I do derivative with respect to lambda, it's just the constraint. So this is just like we did before with standard optimization, right? I set the gradient equal to 0. I get this Lagrange multiplier term, and then I have the original constraint. I have both sets of conditions. Thoughts? Yeah, so we're going to have to set up some kind of KKT system that depends on that's got this guy and the constraint equation. And we're going to have to jointly solve that KKT system for both Q double dot and lambda, right? Okay, we're at time, but can I hint for next time? Oh, why do I keep doing that? Okay, so we will do this. Hooray, we have time. Okay, cool. Excellent. I have a mental block with that. I don't know why. It's ridiculous. I think like, yeah, I must have, I'm pretty sure one of the previous schools I was at had a 1020 class, and I just like, it's forever stuck in my brain now. Anyway, okay, so that's what we want to do. Right now, I have C of Q equals 0. So in like standard optimization terms, right, like if I were doing this, you know, with KKT stuff, I would be ready to go. I'd have like some equation that depended on Q, and this guy depends on Q, and I could solve jointly for Q and lambda. But I kind of can't do that right now, because remember what I'm trying to actually solve for here is Q double dot. And this guy, there's no Q double dot in that guy, right? Okay, so anyone have any ideas? What do I do? Yeah.
Derive.
Right?
Your states.
Sorry?
You derive your states.
Derive meaning what?
Like take the derivative of your constraint.
Yeah, that's exactly right. So what I'm going to do is I'm going to take 2 time derivatives of C of Q. So I get it in terms of Q double dot. Now I have 2 sets of equations, 2 unknowns, Q double dot lambda, and I can set up a KKT system. So that's the move. So here's how we do it. Okay, so we've got d squared c dt squared equals, so first thing we got is we'll do one derivative that gives us partial c partial q q dot by the chain rule, right? So that is, now if I do this again, so this is just my j of q, right? My constraint Jacobian. So if I do the next derivative, I'm going to get j of q, q double dot, which is exactly what we wanted, right? We got this thing in terms of the accelerations now. And then we're going to pick up another term that I'm going to kind of like write in a tortured way to avoid taking a tensor derivative. So it's going to look like partial respect to q of j of q, q dot. So this is really taking partial j respect to q, which is a third rank tensor, but it's contracted with q dot. So this is really like some tensor vector product thing. And that thing chain ruled again times q dot. Cool. So this, remember, I had c of q equals 0. So this thing still has to equal 0, right? Think about it as I took the time derivative of both sides. So the right-hand side stays 0. So that the two time derivatives, this thing also have to still equal 0. Cool. So now I can take this equation, which involves the accelerations, and stack this equation with the dynamics, the manipulator dynamics, and form a KKT system. So if I do that in kind of the most straightforward way, I'm going to get m of q, and then I'll get like a j. So here's, let's write this first. So I've got q double dot, which, and then lambda. Here I'm moving the j transpose lambda term to the left-hand side. So I'm going to get a minus sign on it. So this is going to be minus j of q transpose. So this is m q double dot minus j transpose lambda. So that equals all the other stuff moved over to the right now. So minus c of q, q dot, minus g of q plus f. And then the bottom is this acceleration constraint. So this is going to look like j of q times q double dot equals minus that thing I have up there. So minus partial respect to q of j of q, q dot times q dot. Cool. So now we have this KKT system E thing, and I can solve this jointly for both these guys, and that gives me the dynamics q double dot. So this looks a little weird compared to the KKT systems we wrote before because it's sort of not symmetric because I have a minus sign here. This is just an aside. I can fix that very easily by sticking a minus sign on lambda and solving for minus lambda instead. Typically, when you solve stuff like this in a computer, you do that because symmetric linear systems are nicer to solve than not symmetric ones. And mass matrix is always symmetric, like we said, right? So if I just kind of make that little tweak, then I can make this thing symmetric and it's nicer numerically, but sort of doesn't actually affect anything, you know, otherwise, just kind of a random aside. Okay, questions about this? Another thing you can do if you want to is I can actually massage these two equations around, and I can solve the first one for lambda and like plug it back into the second one, and then solve the second one for lambda as a function of the q's and plug it back in, and I can completely eliminate lambda if I want to, and sort of smush this back to a minimal coordinate form if I wanted to from this. Has anyone seen something like that before in optimization? No? Okay. We'll go there. It's called a Schur complement, if you've ever heard of that. Anyone heard of Schur complement before? Yeah, so that's lets you basically eliminate the lambdas and sort of massage it back into a standard form. Okay, cool. So So that's how you do that. And the last thing we'll do is like a little example of this to show you what it looks like when you do it. So we're gonna go with, we did the carpole kind of all the way through. We're now gonna kind of go back a step and look at the standard pendulum again, because it's nice and easy. And I can actually do all this out by hand without suffering too much. So here we go. So before in minimal coordinates, we had this theta, right? So now just for kicks, and that's all fine, right? We all know how to do that. What we're gonna do instead is we're gonna write down the position of this guy in terms of just standard Cartesian coordinates now, x, y. And that's gonna look like, so now this is super easy to write down. So I get 1/2 mv squared. And then mgy. So like the Lagrangian's like super trivial now, right? It's like stupidly easy to write down. But now I have this constraint that it looks like x squared plus y squared minus L squared equals 0, right? So it's just a circle constraint, right? X squared plus y squared equals L squared, the length of the pendulum. So if I go ahead and write down sort of my standard manipulator stuff, I'm going to get a constant mass matrix now. X double dot, Y double dot, plus my gravity term, potential term, mg. And then I'm going to get my constraint term, J transpose lambda. Here, okay, so J is partial C, partial Q. So here it's partial this guy with respect to X, partial respect to Y. That's 2X and 2Y, right? So that's J transpose lambda. What's the dimension of lambda? What is it? It's one dimensional because I have a single scalar constraint, right? So the Jacobian's 2D because it's the gradient of this guy, but lambda is actually one dimensional. Okay, so this actually looks like this. Okay, so what I need to do now is write down that acceleration level constraint, right? So let's go ahead and do that. So I need to do d squared c dt squared equals d dt of j q dot, which is, if I fill it in, j is 2x, 2y, and then q dot is x dot, y dot. So if I kind of chain roll that again, I get 2x, 2y times q double dot, so x double dot, y double dot, plus 2x dot squared plus y dot squared equals 0. So now if I plug all that together and like write down my KKT system thing, I'm going to get mass matrix, which is this guy, which doesn't depend on Q anymore. I'm going to get minus J of Q transpose J of Q, which is this guy up here, the 2x, 2y thing. This whole thing is times x double dot, y double dot, lambda. And this equals, so 0, the gravity term pulled to the other side, and then minus 2 x dot squared plus y dot squared down here. So I can solve this linear system for all three of these guys, and then I can plug x double dot, y double dot into my dynamics, and good to go. Yeah.
Taking the second derivative of the constraint that makes sense mathematically. Does it also have any physical implications?
Yeah, we're out of time, actually out of time this time. So we're gonna talk about this next time. There's some bunch of fun things to talk about here, including some things related to what we talked about with quaternions and numerical integration and drift and fun things like that. So yeah, I wrote the constraint down at the acceleration level instead of the position level. One of the things that does is get me the constraint force, actually, right? So the second derivative of the constraint is basically going to give me explicitly the constraint force. That makes sense? Which is actually useful in a lot of cases. Like if I, for example, write down, something that's like a robot standing on the ground, I have a constraint that the foot's, attached to the floor. The constraint force is actually going to give me the normal force and friction force of the foot on the floor. So
And
that's,
one interpretation is like you're basically setting some component of the acceleration to.
yeah, that's exactly right. Yeah, that's what I'm doing, right? Okay, yeah, sorry, we gotta go, guys. But yeah, more on this next time. We'll talk about this and we'll do some more numerical stuff again next time now that we've kind of done a bunch more theory stuff.